In the transport industry, most shipping containers are designed in a rectangular shape to cram in every cubic centimeter of profit. However, liquid transport trucks carrying milk, gasoline, and chemicals always feature a cylindrical shape. Rounding the corners means effectively throwing away 20% of the cargo space, slashing billions in profits for capitalists. Not to mention, cylindrical tanks cannot be stacked or transported as easily as rectangular ones. So why are liquid transport trucks always round? That shape is actually the result of meticulous calculations to optimize both profit and safety for every journey. Put yourself in the shoes of a driver. You're behind the wheel of a truck carrying 30,000 liters of liquid hurtling down the road at 90 kilometers an hour. Unlike solid cargo, these 30 tons of liquid are constantly shifting with every movement of the vehicle. When you slam on the brakes at an intersection, the truck stops, but the 30 tons of liquid will surge forward like a tsunami, slamming into the container's walls. Inside a rectangular tank, all that force would smash directly against a flat wall, creating massive leverage and flipping the entire truck over. More seriously, even if the truck doesn't flip, the outward pushing force of the liquid is enough to tear apart the welds at every sharp corner of the tank. But with a cylindrical tank, the curved surface allows the liquid to slide, dispersing the force in multiple directions. The curved sides also allow the bottom of the tank to sit nested deep between the chassis beams. As a result, the truck's center of gravity is drastically lower, reducing the leverage effect much more efficiently than a rectangular tank sitting high on a flatbed. The perforated bulkheads, baffles, installed inside the tank also help break the liquid's surge force right from within. All three of these mechanisms work continuously to neutralize the surging tsunami. The force dispersion capability allows a cylindrical aluminum shell just 5 millimeters thick to withstand the immense pressure of the massive liquid load. However, the movement of the liquid is only part of the equation. Another equally dangerous situation can occur when the truck is unloading. A high-capacity pump can suck out thousands of liters of fuel per minute. If the breather valve on top of the tank gets stuck, the internal pressure drops rapidly, creating a vacuum environment. Just like when you stick a straw into a juice box and suck hard, the box instantly crumples. Under the immense weight of atmospheric pressure, the metal plates of a rectangular tank would bear the brunt of a massive crushing force. That very pressure would cause them to implode and collapse inward in less than a second. Meanwhile, a cylindrical tank with its continuous 360-degree curved surface is a different story. Thanks to its arch-like structure, the crushing force is deflected and slides along the tank's hull, forcing the metal molecules tightly together into a solid cylinder. As a result, a round tank is practically immune to implosion, unless exposed to a complete vacuum for a prolonged period. Thus, the cylindrical shape is a near-perfect solution to ensure liquid transport goes off without a catastrophic hitch. Furthermore, the round tanker design also solves a brutal economic equation. At first glance, a rectangular tank has one very obvious advantage. With the same length and width, it maximizes space utility, eliminating the lost volume at the curved edges. However, to carry liquids safely, a rectangular tank would require extremely thick steel plates and heavily welded reinforcement frames at every corner. Consequently, the tank balloons into a massive deadweight, weighing 2 to 3 tons more than a cylindrical one. In the logistics industry, legal weight limits are an uncrossable red line. When an empty tank is 2 to 3 tons heavier, you lose 2 to 3 tons of payload capacity on every single trip. If a truck runs an average of 300 trips a year, consistently for its 15-year lifespan, that's 13,500 tons of lost cargo. Even at a rock-bottom freight rate of $50 per ton, just one poorly designed truck would burn through nearly $700,000. And that's just operational loss. Manufacturing cost is another equally crucial factor. The manufacturing process for a cylindrical tank is straightforward. Feed an aluminum alloy plate through a rolling machine to curve it in just 10 minutes. The process is relatively fast, stable, and easy to automate. Conversely, building a rectangular tank requires cutting 6 massive steel plates, perfectly aligning the angles and adding reinforcement costs. Every step in this process inflates production time, labor costs, and the risk of technical flaws. Not to mention, over long-term use, the sharp corners and heavily welded joints are the first to degrade, leading to much higher maintenance costs. Additionally, tank cleaning operations are significantly impacted. For liquid commodities, fully sterilizing the tank after every trip is a mandatory requirement to avoid ruining the next batch. Washing a square tank is like cleaning a greasy plastic food container. The sharp corners become traps for stubborn residue and bacteria, making thorough cleaning a nightmare. A cylindrical tank, however, allows the liquid to drain almost completely and makes the sanitation process exponentially faster and more efficient. Thus, balancing both mechanical engineering and long-term cost efficiency, the cylindrical tank has become the absolute gold standard in liquid logistics. In fact, the cylindrical design of tanker trucks has appeared throughout history, taking on various forms each time. Hundreds of years ago, oak barrels assembled from curved staves were used to transport wine and ale across oceans. This design allowed the barrels to withstand the outward pressure of the liquid as the ship swayed, surviving brutal ocean voyages without bursting. Today, the exact same principle is applied everywhere, from tiny soda cans to submarines operating deep at the bottom of the ocean. All these objects obey one universal rule: curved surfaces drastically reduce the risk of structural failure. Clearly, throughout history, engineers have continuously harnessed the power of round containment to apply to their designs. Ultimately, that cylindrical tanker truck you see on the highway today is the ultimate optimization of both science and economics. When a design reaches this level of perfection, it remains virtually unchanged. But in the future, will the invention of smart supermaterials cause the cylindrical tank to finally disappear? And if you're curious about familiar things that few truly understand, leave a comment with the topic you'd like me to explain next. Thanks for watching.